Let's say you're writing a server that calls a database and retrieves all your user records. As your user count grows, you notice the database is taking longer to return the query results and your server's memory utilization is spiking. What's happening? Well, when we query the database, it has to fetch all the matching rows, put them into a temporary table called the results set, and then return that over the wire to our server. Our server then loads all that data into memory. As the number of rows gets bigger, our database will take longer to fetch all the rows and send them back, and our server has to use more memory to store the data too. So how do we efficiently read data as our data gets larger and larger? This is where pagination comes in. Instead of querying our data all at once, we query it in chunks. Let's call each chunk a page. We also keep track of what page we're up to, so we know where to continue reading from. So now the question is, how do we implement it? The most common, easiest to implement, and least performant option is offset pagination. Imagine we're limiting each page to n records, and m is our current page number. When we query the database, we take n records while skipping the past m-1 times n entries. So if we're grabbing 20 records at a time and we want to query the third page here, we will skip the first 40 records. Intuitive, right? Sadly, it gets slow. Even though we're skipping records from the server's perspective, the database still has to fetch all the records we're skipping to get to the next page. This is known as a scan operation, which means we're not really reducing load on the database at all. It's also straight up incorrect sometimes. Imagine your user is about to navigate from page 1 to 2, and right as the navigation is occurring, a new record is inserted into the table. This causes all the results to get shifted down, and we'd end up returning a duplicated record. The more efficient solution would be to use keyset pagination, also known as cursor pagination. Keyset pagination is also simple. We just use a where statement to skip rows by using a non-null column with an increasing value like the created at timestamp, and an additional ID column for tie breaks. This column, or a combination of columns, is known as the cursor for our pagination. The last important requirement is that we need to order our results on our cursor columns using an order by statement. And this ordering must be unique, otherwise the same cursor value could give us different rows. One lingering question remains: how do we know when we've exhausted all of our pages? Or in other words, what is our stop condition for pagination? Well, it might feel like a bit of a hack, but a commonly used technique is to always query an extra record. For example, if the page size is 10, then query for 11 records. If the 11th record also comes back, then we have more pages to go. Otherwise, we've reached the end and we can return a null value for the cursor. Unfortunately, keyset pagination does have one drawback, as you might have noticed, and that's that it doesn't support random access to any given page. The cursor can only skip forwards one step at a time. It is possible to also paginate backwards though, and we do this by maintaining two cursors, one for going forwards and one for backwards. For backwards navigation, we simply reverse the where comparison and order by statement. To make this implementation even more efficient, we can use an index on the cursor columns. In SQL databases, using a where statement on an index column leads to a seek operation, which is super fast and is a lookup directly to the point where data needs to be read from. Now let's look at some patterns in API design and UI design when using pagination. Typically in REST APIs, when a GET endpoint supports offset pagination, the URL for that endpoint accepts two query parameters, a page number and a page size. For keyset pagination, the cursor is usually sent as a base64 encoded object that includes the last used cursor values. The reason for encoding is to hide the implementation detail or metadata from the client. From a UI perspective, if you're using offset pagination, then it makes sense to let users pick any page to go to. But for keyset pagination, it's very common to implement the infinite scroll pattern, where you let users scroll down on the page and load the next page once the user is finished going through all the current items. As a side note, a funny thing I noticed while working on this video is AI coding assistants love going for offset pagination for some reason. Maybe because it's overrepresented in the training data or it's the easiest to implement, but when I asked Claude and Gemini to implement pagination, both of them reached for offset pagination, even though it's provably not the best solution most of the time. It goes to show that as engineers, we still should be aware of the trade-offs between different implementation choices. Pagination is a very strong technique for improving performance while still maintaining a good user experience. At the same time though, it doesn't mean refactoring all your endpoints to use pagination. It has its use cases, but its implementation introduces extra overhead and cognitive complexity to your codebase. Don't reach for it until you can prove that you need it. Otherwise, that's just premature optimization. And as the saying goes, it is the root of all evil.